Welcome to part 6 of the MOJO project. This video is about the origin of Earth's water. Let's start with an overview of the water distribution in the solar system. We receive from the asteroid belt several kinds of meteorites. Some of them, called carbonaceous chondrites, contain quite a significant amount of water. Several percent of their mass is made of water. And these meteorites come from carbonaceous asteroids, primarily located in the outer asteroid belt between 2.5 and 3 AU. Actually, there are some carbonaceous asteroids which seem to contain even more water than carbonaceous chondrites. For instance, we have what we call main belt comets. These are carbonaceous asteroids that become active like comets every time they pass at perihelion. And even Ceres, which is the biggest asteroid in the asteroid belt, also a carbonaceous asteroid, seem to have 30% water by mass, according to the results of the recent Dawn mission. From the inner part of the asteroid belt, we receive instead two other kinds of meteorites. Ordinary chondrites contain a fraction of a percent of their mass in water, and dense-type chondrites are even drier, less than 0.1% of their mass is in water. And these meteorites come from asteroids located between 1.5 and 2 AU for the dense-type chondrites, 2.5 AU for the ordinary chondrites. So all this data suggests that there is a correlation between the water content of planetesimals and their location with respect to the distance with respect to the sun. We have seen in part 5 that the Earth is quite dry, but compared to this correlation, the Earth is actually richer in water by 1 or 2 orders of magnitude compared to what we would expect from this correlation. So this suggests that the Earth accreted its water from planetesimals that form further out in the solar system. And these planetesimals could be carbonaceous asteroids or maybe even comets. Isotopes can give us some important information to discriminate between carbonaceous asteroids and comets as the main deliverers of water to the Earth. In fact, there are two molecules of water. The most dominant molecule of water is H2O. It is made of one atom of oxygen and 2 atoms of hydrogen. But there is also another kind of water molecule, which is called HDO. It's made of 1 atom of oxygen, 1 atom of hydrogen, and 1 atom of deuterium, which is a particular kind of hydrogen which has 1 neutron in addition to the proton. So when we analyze the water on Earth, we find that 1 molecule of water out of 6,667, it's made of HDO. And if we analyze the water in carbonaceous meteorites, we find the same. 1 molecule of water out of 6,667 is made of HDO. Instead, when we analyze the water of most comets, we find that 2 molecules of water out of 6,667 are made of HDO. So this suggests that carbonaceous asteroids are the main contributors of water to the Earth. As a matter of fact, there are some comets which also have the correct HDO-H2O ratio, but these comets have different ratios for other isotopes, for instance, for nitrogen isotopes. In addition, numerical simulations show that only 1 comet out of 10 million hits the Earth. So their contribution to the delivery of water or any kind of material is quite negligible. So all together, these data clearly show that water comes from carbonaceous asteroids. So the important question is, how did carbonaceous asteroids deliver their water to the Earth? In the MOJO project, we show that Jupiter's migration and/or growth was the key for the delivery of asteroidal water to the Earth. We have seen in part 5 that carbonaceous planetesimals are believed to have formed beyond the orbit of Jupiter. So we need to understand how they could go from beyond the orbit of Jupiter to the growing terrestrial planets. And we've seen in part 4 that we have 2 models for that. In one model, called the Grand Tack model, Jupiter had a phase of outward migration. By migrating outward, Jupiter encountered these planetesimals originally located beyond its orbit and scattered some of them on eccentric orbits that intersected the forming terrestrial planet ring. Now, these orbits, if they stayed in this configuration, would still cross the orbit of Jupiter. Then Jupiter would eject these planetesimals in a very short time before that they have a chance to deliver their material to the growing terrestrial planets. But Jupiter continues its outward migration, and this decouples the orbit of Jupiter from the orbit of these scattered planetesimals. So these planetesimals can live much longer, and thus they have a chance to collide with the growing terrestrial planets and deliver their water. We have seen in part 4 that it's not sure that Jupiter migrated outward. Maybe Jupiter stayed more or less in situ. In that case, the planetesimals beyond its orbit could have been destabilized and scattered into the inner solar system during Jupiter's growth. And in this case, the decoupling between the orbit of these planetesimals and the orbit of Jupiter would have been due to gas drag. And then once decoupled, again, these planetesimals would have collided with the terrestrial planets and delivered their water. In this scattering process, some planetesimals formed originally beyond the orbit of Jupiter could also have been scattered on more circular orbits, typically of the asteroid belt. And this is how we believe carbonaceous asteroids that we see today in the belt reached their current position, even though they formed beyond the orbit of Jupiter. So we can say that the asteroids that deliver the water to the Earth and the carbonaceous asteroids that we see today in the belt are actually siblings coming from the same parent population originally located beyond the orbit of Jupiter. This animation shows how the water is incorporated in the growing terrestrial planets. The terrestrial planets primarily form from a ring in the inner solar system made of planetary embryos, here illustrated in green, and dry planetesimals, here depicted in red. But there are also these water-rich carbonaceous planetesimals scattered in by Jupiter, either through migration or growth, on eccentric orbit in the inner solar system. And now we will see an animation showing the evolution of this system where the orbits are represented as a function of their size, so the sine major axis on the horizontal axis, and the eccentricity, so the shape of the orbit as indicated in this scheme on the vertical axis. So as the animation is running, we see that the embryos rapidly collide with each other, forming two major planets, and then there is a stranded embryo further out at about 1.5 AU. So these three planets that this simulation produces correspond quite well to Venus, Earth, and Mars. And the blue dot at the center of each planet shows which mass of the planet has been, which fraction of the mass of the planet has been accreted from these water-rich planetesimals scattered in by Jupiter. And we see that not only the Earth, but every terrestrial planet should have accreted a comparable budget of water. And this water is accreted during the growth of the planet, not just at the end, once the planets were fully formed. MOJO!